Today we are beginning our unit on sequences and series, and today we're talking about just the basics of sequences and series. So first of all, a sequence is very simply a list of numbers in some pattern. That's all it is, a list of numbers in a pattern. They are separated by commas. A sequence is a list of numbers separated by commas in some pattern that allows us to know what the next term will be. This sequence is finite because it ends. This sequence is infinite. That dot 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 means it continues forever. So we can have a finite sequence or an infinite sequence. We denote a sequence's terms with a sub n or b sub n or m sub n or whatever, something sub n, where n is called the index. We normally start with an index of 1, but sometimes it is convenient to have our initial index be 0. And sometimes they will tell us some other number to let our index begin at. So we have to be flexible when it comes to that index. But for most of the time, if they don't give me what the index begins at, I'm going to let my index begin with 1. There are two types of formula that we can use to describe a sequence. And the first is a recursive formula. A recursive formula uses previous terms to arrive at a new term, to obtain or arrive at the new term. Okay, a famous sequence called the Fibonacci sequence is based on its previous terms. This is the Fibonacci sequence. The first two terms are ones, but after that, to get to any new term, you add the previous two terms. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, etc. To get to any term, you add the previous two terms. So written as a formula, if I tell you that a sub 1 is 1 and a sub 2 is 1, then for n greater than 3, a sub n is the sum of the previous two terms. So the previous term would be a sub n minus 1, and we add a sub n minus 2. These are the two terms in front of that term. With a recursive formula, we must be given at least one term of the sequence, depending on how many terms it's based on. However many terms it's based on, we need to be given that number of terms to obtain a new term. Okay, what are the first four terms of the sequence with first term negative 3 and a sub n equals a sub n minus 1 plus 7, where n is greater than or equal to 2. So the first term is 3. What would the next term be? Well, this is telling me to take the previous term and add 7. If I take this term and add 7, I get 4. That was negative 3 plus 7. And now to get the next term, I take the 4 and I add 7. That will be 11. The next term would be 18 because we're taking 11 and adding 7. So those are the first four terms of the sequence. All right, so that's a recursive formula. That's the first way that we can describe a sequence. What is more normally used, however, is an explicit formula, because with an explicit formula, we don't have to know any preceding term. This formula will allow us to find a term only being given which number term we want to find. Okay? For this one, if we wanted to find the 7th term, we would have to know the 6th term, right? In this one, to find the 7th term, we can just put in a number for n. So let's write the first 5 terms of each of these sequences. So the first term is when n is 1. So when n is 1, I will have 1 over 4. That's my first term. When n is 2, I'll have 2 over 5. When n is 3, I'll have 3 over 6. When n is 4, we'll have 4 over 7. And I realize I could reduce that if I needed to. For a multiple choice question, I could easily reduce that, right? Oh, it said 5 terms. I'll give them one more then. When n is 5, we'll have 5 over 8. Okay? Let's do the same thing over here. When n is 1. When n is 1, I have negative 1 to the 2nd power. What is negative 1 squared? That's 1 over 1. So my first term here is 1. Okay? When n is 2. When n is 2, I'll have negative 1 cubed. That's negative 1 over 2. Next up, when n is 3, I'll have negative 1 to the 4th. I'm back to a positive. My bottom is 3. And take a look at the pattern that's going on here. What would be the next term? Well, it's going to be negative. And what's my new denominator? A 4. Sometimes I'll carefully plug in n values until I see the pattern. Once you see the pattern, stop plugging in n values and just use your pattern. The next term here would be 1 over 5. The next term would be negative 1 over 6, etc. Okay? For this one, the first term will be 1 squared plus 1. That's 2. The next term will be 2 squared plus 1. That's 4 plus 1, or 5. The next term, 3 squared plus 1. That's 9 plus 1, which is 10. Next term is 16 plus 1. Next term is, I almost wrote 25. Next term is 25 plus 1. Like that. Okay? Alright, this is a good time to talk about factorials. The definition of a factorial. If n is a positive integer, then n factorial is defined as, look at what n factorial is. It has an the notation for factorial is this exclamation mark. Okay? So n factorial is defined to be 1 times 2 times 3 times 4 times 5 all the way up to n. As a special case, 0 factorial is defined to be 1. Okay? You need to know that 0 factorial is 1 by definition. Okay? Alright, let's do some examples just with factorials. Okay, 2 factorial would be, in the definition, they always start with 1 and end at n. Oh my goodness. Start with 1 and end with n. I like to go backwards and start with n and end with 1. Alright? So when I'm given 2 factorial, I think of that as 2 times 1, which is just 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial, 4 times 3 times 2 times 1, which is 4 times 6, and so 24. 5 factorial is 5 times 4 times 3 times 2 times 1. That is 4, watch this, this is 4 factorial times 5, right? This was 4 factorial. If I multiply that times 5, I'll get 5 factorial. And 5 times 24 is 120. We use factorials in calculus a bit, so I have these memorized. I have the next one memorized too. 6 factorial is 720. I have that memorized as well. So factorials get large very, very quickly. 13 factorial is this. We're only at 13, and we are at 6 billion something. 20 factorial. 20 factorial is this number. It's huge. Factorials get large extraordinarily fast. Okay? If you multiply this by 21, you'll get 21 factorial. So it's 21 times this big. Huge. It gets huge really, really fast. Okay, let's do some computations here. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 4 factorial is 4 times 3 times 2 times 1. How does this reduce? Well, I see all these 4, 3, 2, 1 divided by 4, 3, 2, 1. Those reduce out. 6 goes into 2, or 2 goes into 6 3 times. I'm left with 1 on the bottom and 15 on top. So that is just 15. Okay, number 10. Up here is n factorial. Here's n plus 2 factorial. You agree that n plus 2 is bigger than n. I'm going to start there. So I'm starting on the bottom. N plus 2 times the next number down. What's the next number down? N plus 1. What's the next number down? N. And then n minus 1, n minus 2, etc. That's n factorial. Why am I writing it like that? Because I know what's on top. I have an n factorial on top. So the n factorial on top reduces with that n factorial, leaving a 1 on top, and n plus 2 times n plus 1 on the bottom. Excuse me. So what about number 11 here? Which is bigger? Start there. The bottom is bigger again. So this is n plus 1 times the next number down. If you subtract 1 from this, you get just n. If you subtract 1 again, you get n minus 1. And then you keep on subtracting 1 until you get down to 1, but I'm stopping there because I know what's on top. So once again, these reduce, leaving a 1 on top, and n times n plus 1 on the bottom. So that's how those factorials reduce. Alright, let's talk about series. The sum of the first n terms of a sequence, the sum of the first n terms, is represented by this summation notation. We use the capital Greek letter sigma for the sum of terms. Okay? This I is called the index of the summation. We're starting I at 1 because there's a 1 right there. Okay? We're ending I at n. Okay? So n is the upper limit of the summation, 1 is the lower limit of the summation, and this would be a sub 1. We'll put 1 in for n, that's a sub 1, plus, put 2 in for n, put 3 in for n, etc. And you keep on going until you get to n. So right here, I is going from 1 to 5. Okay? 1 to 5. The first I is 1, so that would be 3 times 1. Plus, the next I is 2, so that would be 3 times 2. The next I is 3. 3 times 3, and we keep on going until we get to an I value of 5, because they told me to stop when I was 5. So this is 3 times, do you agree that every term has a 3 in it? So I'm going to factor that 3 out, and that is 3 times 1 plus 2 plus 3 plus 4 plus 5. And that is 3 times 3 plus 3 is 6, plus 9 is 15, and 3 times 15 is 45. There is a function on your calculator. You guys, this test will be all no calculator. However, I want you to know where this is on your calculator so you can check yourself on these. So under F2, F2, if you go to F2, number 2 is the summation. So number 2, okay, this has an I. It's just easier for me to get to the X, so I'm going to use an X instead of an I. I'm going to go from 1 to 5, and it's 3 times I, so I'm going to use using X for I, and I get 45. So there's a way to check yourself on those. Alright, let's do this one. We're starting K at 3. The first K is 3. So my first number will be 1 plus 9. And then I will add 1 plus 4 squared. My next number will be 1 plus 5 squared. My next number will be 1 plus 6 squared, and I will stop there because I've reached my top limit. Okay? So this is 10 plus 17 plus 26 plus 37. And when you add all of those together, I just realized I had a mistake on my other notes. When you add all of those together, you're going to get, let's add those together. So 7 and 6 is 13. 13 plus 7 is 20. So we add that 2. 3, 4, 5, 6, 7, 8, 9. So this is 90. Okay, number 14. Oh, and we could check that on our calculator. Let's go and check that on our calculator. Why not? Got this here. So I go to my F2, number 2. F2, number 2. X is going from 3 to 6. And my equation is 1 plus x squared. And it is 90. Check. Alrighty. By the way, how many terms were in that sequence? From 3 to 6, how many terms were in it, in that series? There were 4 terms in that series. When we went from 3 to 6, there were 4 terms, not 3. There were 4. Okay? FYI. We'll need that later, tomorrow. Or maybe coming up soon. I think it's coming up soon. Okay. Number 14. We're starting n at 0. We're starting n at 0 here. So my first term is 1 over 0 factorial. My next term is 1 over 1 factorial. And then 1 over 2 factorial. And 1 over 3 factorial, etc. Until we get to 8. Yes. Okay, what is 0 factorial? 0 factorial is 1. 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, that's 6. 4 factorial, if I multiply 6 times 4, I get 24. That will be 4 factorial. Oops, plus. 5 factorial, if I multiply 24 times 5, I get 5 factorial. 6 factorial, if I multiply 120 by 6, I get 720. That's 6 factorial. If I multiply 720 by 7, I get 5040. That is 7 factorial. If I multiply 5040 times 8, I get 40,320. Look how big factorials get very quickly, right? Okay. By the way, if I took these numbers and I added them all together, let's add those together. There's a reason I'm doing this. I get, well, you know what? Let's check this on our calculator. Let's do second to x is going from 0 to 8. And that is 1 divided by x factorial. X factorial. The factorial, is it under F2? Let me see if it's under F2. Oops, F2. Hang on. That's not going to do it for me. Let me go back here. Insert. Okay. Alpha F2. Is factorial here? Oh, it is. It's number 9. F2 has a bunch of these. So number 9. And I get that. So if I added all these up, I would get 2.71827,877. And that looks really familiar to me. You guys, look what E is. E is 2.718281828. So those are really similar. They're equal up until the 5th decimal point, or the 5th place after the decimal point. If I took this and I used some more numbers, let's not stop at 8. Let's go to something bigger like 15. Look at that. If we went to infinity, if we took the sum from 0 to infinity of 1 over n factorial, that would equal E exactly. Okay? FYI. You don't need to know that. It's just an interesting observation. All right. Definition of a series. Consider the infinite sequence. The sum of the first n terms is called a finite series, or the nth partial sum of the sequence. Okay? Oh my goodness. This will be corrected on yours. There should be some pluses here. They're all pluses. Alrighty? Oh, down here as well. I can tell I cut and pasted things, but those should all be pluses. Okay? And this should also be the word series, not sequence. I'll fix that on yours when you get it. Okay? So, a finite series stops. You can find the sum of just the first so many terms. An infinite series does not stop. It goes on forever, and you would have an infinity right there. Let's consider this series. Let's find the third partial sum. What is the third partial sum? Well, the third partial sum, if we're starting n at 1, it will go to 3. And that would be 3 over 10 to the first, plus 3 over 10 squared, plus 3 over 10 cubed. Right? You guys, this is 0.3, and I'm adding 0.03, and then I'm adding 0.003. What is that? That is 0.333. That's what that is. Find the sum of the entire series, the entire infinite series then. Well, that would be 0.3 plus 0.3 0.03, sorry, plus 0.003, plus 0.0003, and that would keep on going. That would be 0.333333333 forever and ever. What is that number? That number is 1/3. So this is 1/3. Okay? Alrighty, a little introduction to basics of series and sequences.